So I was talking about the history of the human's ability to detect exoplanets. Okay, so as I said, going back to the early 1990s, before the early 1990s, we simply speculated that there were planets around other stars. I mean, there are literally billions upon billions of stars just within our Milky Way galaxy. There's billions upon billions of other galaxies out there. So we thought for sure there are other planets out there, but our ability to detect them really started in the early 90s, and really it was the advancement of computer technology that first allowed us to do that. And as I mentioned in the last video, by the vast majority of the detection of these planets is indirectly, okay, and I'll explain that in a little bit. There have been just a small, like a handful of direct observations of some of these exoplanets, but that's very rare. That's a very rare situation. Things have to be just right for that to happen. All right, but we'll talk about the way we normally see, or have not see, detected should be the proper word. All right, so the first, and this is actually going historically correct. The first way that we detected planets was from the wobble of the star. So because of Newton's third law of motion, that for every action force there's a opposite and equal reaction force. When a planet goes around its star, it's pulling the star in one direction and pulling the star half of its cycle later, half of its orbit later, in the opposite direction. Now, if the planetary system is such that we can, if the angle from our perspective in the Milky Way is such that we can actually detect that wobble. That is, if it's, let's say, the planetary system is exactly at a 90-degree angle, which is pretty unlikely. That's usually at some arbitrary angle, but let's say at a 90-degree angle from our perspective, then what we do is we can actually, using what's called the Doppler effect, the light from the star will get shifted in the Doppler shifted. It'll either be shifted towards the red or shifted towards the blue end of the spectrum, depending on whether the thing is coming towards us or moving away from us. Moving away is called a red shift. Moving towards us is called a blue shift. Whether it's in the blue or the red is just what it's called. All right, so this is what we saw, originally, or what we were able to detect with computers and the advanced telescopes in the early 1990s, is that we would actually see the wobble of the star be periodic. And so that's a really important thing, that it would repeat itself, and it would repeat itself. Sometimes it would just take a few days to repeat itself. Sometimes it took longer, but we would see these repetitions. And in some situations there would be multiple wobbles going on at the same time with the same star. So what that was finding is you have a star system with multiple planets, and that's the very first way that we were able to detect planets around other stars. All right. The next method is a much. This is, I mean, the wobble method is still used. Don't get me wrong. It's still used. It's still very much important to us. But in science, we always want to have multiple methods of measuring the same thing when possible, when the technology is in existence. And of course, this method, called the transit method, is very, very popular now. This method is used with ground-based telescopes, but one of the areas where this has been, and I mentioned the two spacecraft, where this has been used a lot is spacecraft that we've launched into orbit around the Earth and have basically looked at a star. Oh, well, let me first go and explain what the transit method is. So if a planet passes in front of its star, now it doesn't have to go across like the center of the star, just part of it. Okay, so if a planet is doing this, where it's just exactly at a 90-degree angle with respect to us, you can't use the transit method. The transit method won't work. The planet has to pass in front of its star, and so what happens when the planet passes in front of the star, that's called a transit. When that happens, the starlight dips a little bit, just a little bit. Okay, not very much at all. And in fact, the reason that this method wasn't used for the last 50 years is because we didn't have the technology to be able to detect that slight dip in the intensity of the light, in what's called the luminosity of the light. So now we can actually, with more modern equipment, more modern technology, we can detect that, and this is the method that is more in vogue nowadays than the wobble method. Although, let me be clear, the wobble method is still used. So there's actually another way that we detect planets called microlensing. I'll get into that in just a little bit. But the first spacecraft that utilized this was a mission called Kepler, which is no longer functioning. The Kepler spacecraft, it's still out there. It just the gyroscopes that held the telescope locked into one portion of the sky. The final one failed, and we basically can't use that telescope anymore, or that spacecraft and the telescope that was on it. Nowadays, there's a more modern version and a more actually a better equipped space mission called TESS. That in fact the T stands for transit, right? It's I forget the exact what the acronym stands for, but it's like something like transit, exoplanet, something like that. Anyhow, something survey, if I remember correctly. Anyhow, so that spacecraft has been active for the last few years and is continuing to be active. Hopefully we'll get at least a decade. With the Kepler mission, we got about a decade, more than a decade actually, more than 10 years of data from that. In fact, we're still finding planets or detecting planets from Kepler's original data. But like I said, the TESS mission is currently used. And of course you can also do this with some ground-based telescopes. Although what's called the seeing, which is a technical term in astronomy, the seeing has to be just right to be able to do this. From ground-based telescopes, it's much easier to do the transit method using spacecraft that are designed to do this. All right, so that's that. Let's see. Is there a thing on microlensing? And so this is like I said, this is a very rare situation where we have a direct picture of a planetary system. You can see that this is where the little arrows are showing where the planets are. So this is direct evidence, an actual photograph of this little system, which doesn't have a very interesting name, but that system, the planets are large enough that we can, and the system itself, the star system, is close enough that we can actually measure this directly. But that's, like I said, this is a very rare thing. All right, let's see. So more than 3,500 exoplanets have been discovered, and there's over 5,000 that are what we would call very strong candidates. And this is the thing that was really eye-opening, even in the early days of exoplanet discovery in the mid 1990s, is we found a lot of what are called cold Jupiters and cold Neptunes, and they turned out to be really close to their host star, right? The star that they're orbiting around. Some of the orbits are highly eccentric. Remember, eccentricity is a measurement. The less the eccentricity, the more circular the orbit, and the more eccentric. Like, for example, very eccentric orbits in our solar system would be comets. Kind of like a big egg shape. That would be the very eccentric orbits. So we're finding these eccentric orbits in other star systems. This is actually showing a plot of, let's see, what is this? This is shows the mass and the semi-major axis. Remember, so this would be the semi-major axis of one, and I'm sorry. Here's this. This is the horizontal axis is showing the semi-major axis. But notice we're finding, and these are the masses compared to Jupiter, Jupiter-sized masses. So we're finding, we find some of these things are many times the mass of Jupiter. Let's see. And then some of them are less massive than Jupiter. But notice we get this huge number of these, Jupiter-sized worlds closer to the orbit of, closer than we are to the Sun, right? Remember, 1 astronomical unit is the distance from us to the Sun. So they're much closer to their host star than we are to our Sun. Now, thus far, we haven't found any planets exactly the size of the Earth, right? Or smaller, obviously, smaller. We speculate that there's a whole bunch of planets out there that we just don't have the technology to be able to detect. Hopefully, in the next 10 years, there's more space missions planned. If the money is available, certainly. All right, and so we find lots and lots of exoplanets that are certainly within the orbit. The distance between the Earth and the Sun. So we remember we call that 1 astronomical unit. It's just a standard unit. And of course, we find some of these exoplanets outside the orbit. Now, we do find some Earth-like worlds, or Earth, the same mass. They actually call them super Earths. So maybe 2 or 3 or 4 times, something like that. It could be like 2.4 times the mass of the Earth. All right, so let's see. So we see a bunch of these. So they've actually distinguished the ones that are really close to their star. So if it's within 0.15 astronomical units, those particular planets, exoplanets, are called hot Jupiters, and then ones that are further are just, normal Jovian type worlds. We find, let's see, stars with compositions like our sun are much more likely to have planets, and they show the